Hello everyone, this is my real-time rendering final project, charcoal rendering and shading with reflections. I will divide my project into three parts. First is the part of phone illumination and spotlight. We need ambient, diffuse and specular light to consistent. Ambient light ensures no area is pitch black, providing a base level of illumination. Diffuse lighting gives objects their vivid color when light strikes them. You can see it in this part. It is the base color on it, and which this kind of diffuse light is depending on the angle. Last is a specular lighting. It adds the shiny spots you can see on polished or wet surface, giving a sense of glossiness. You can see the shyness here is provided by the specular. Then I found that in charcoal rendering, spotlight has a better result compared to direct light because spotlight has the effect of attenuation. You can see the texture actually changed because of the attenuation of the light of the spotlight, and which the increasing of the distance, the light effect will decrease and it will change the texture of the surface, which will fit my requirement perfectly. This code calculates sorry mm, this code calculates how the light from a spotlight diminished over distance, combining the effect of the light's intensity, its reach, and the shadow it casts. The attenuation parameter measures the light's reduction based on the distance from the light source, factoring in constant uh, linear and quadratic rates of fall off. The light factor adjusts the final light intensity on a surface, considering whether it is shadowed. Secondly is the part of the shadow mapping. First, we have to set up the shadow map, and which I realized the part in this function. And I actually mentioned illustrated specifically in my report, so I will only show the code. Next is the key point where we need to use the Dips shader to do the calculation. Mm, In this function, the render Dips map sets up the viewport and binds the frame buffer object, which I called it FBO, to prepare for Dips map generation. It uses GLU's program to switch to the shader program specifically designed for generating Dips map. Then the part of the render scene from light view function is called to render the scene from the perspective of the light source. This function iterates through all objects in the scene, such as cubes, plants, books, and apples. Apply their position. You can see it actually here. Um, uh, this function iterates through all the objects and applying their position, rotation, and scale transformation, and then render them into the into the Dips map. You can see this part is using my Dips shader, and this is the vertex shader of the Dips shader, and it is used to calculate the position of the vertex in the view of light source. Next, I will transfer the data into my fragment shader to do the rendering. In this part, I will use the shadow calculation function to calculate the shadow and decide if the fragment is in the shadow. And in this function, it is actually using the shadow mapping and percentage closer filtering, which can help me um, makes the edge of the shadow become softer. PCF technique, which is the technique I mentioned just now, is a method which can softens the shadow's effects by sampling multiple neighboring dips value from the dips map. In the code, a loop iteration, you can see it's here, a loop iteration over the points surrounding the current fragment in a 3 grid, comparing each point's dips to the dips of the current fragment to determine whether the fragment is in shadow. Through this process, I'm able to a shadow variable is calculated for each fragment, which then determines its illumination condition, allowing the rendered scene to exhibit more realistic lighting and shadow effects. In my fragment shader, I implement barycentric shaders using the barycentric basis function for charcoal drawing, leveraging 0 degrees 0 degree B splines basis functions. The mathematic framework allows us to determine the rendered color of a point, which I'm using this function. The function here is actually the rendering equation. By summing up the products of basis function BT and the control texture, these control images are pre-designed textures representing different levels of light intensity that correspond to the qualities of charcoal drawing. You can see this light control image from darkness to lightness. Based on the light and shadow information calculated for each fragment, the shader decides which of the 9 control texture to blend. If a fragment is well lit, a lighter texture is selected, and vice versa. You can see the surface become darker, which the shader decided to use the darker texture in it. Because I set another overhead light source, and you will see it become a little bit lighter because it easy to us to do the observation, and this is the original one. You can see it's totally dark. And for shadowed fragments, a darker texture is used. It may not be observed clearly, but right now you can see. To achieve the soft, smooth transition characteristic of charcoal artwork, we perform linear interpolation between 2 textures. You can see here, based on the brightness, to decide which texture I'm going to use, then using the linear interpolation to blend these 2 textures. The blending is dependent on the calculated brightness, which factors in the shadow and spotlight effects along with the phone illumination models, ambient, diffuse, and specular components. And this approach results in a surface appearance that simulate the charcoal texture under varying lighting conditions. And this is my real-time rendering final project, charcoal rendering with reflection shaders. And thank you for listening.